It's a great pleasure to be here. Can you hear me in the back? Okay. There's no amplifier, so I hope it's going to be okay. What's that?
A bit louder would be great.
A bit louder. Okay. I'll try, but keep reminding me because I won't remember forever. So I'm going to be talking about supersymmetry and try to give you an introduction to supersymmetry and supersymmetric field theories in general. And I want to start with a quick poll and see how many people here had a course on supersymmetry that they actually took. Okay, thank you. So some fraction. And so I'm not going to assume any prior knowledge of supersymmetry. And so this is going to be a little tricky because for some of you, it's going to start at a very basic level. For others, it might be just the right level. But we'll see. I mean, we'll see how far we go. And hopefully, even those of you who've seen supersymmetry before can get something out of this. So let me start with a little bit of kind of background and some sort of motivation. So I think most of us, when we think about supersymmetry, the first thing that comes to mind is naturalness. But it's no secret that there's no hint for supersymmetry at the LHC. And I think that something that we should bear in mind is that there's nothing new about this. I mean, supersymmetry is a very mature field. And it would have been very natural to expect it to show up in lots of previous experiments at LIP, at the SLC, at the Tevatron, in lots of experiments looking for flavor violations, electric dipole moments, magnetic dipole moments, and so on and so forth. And there's no evidence for supersymmetry. And so the question is, why have people been thinking about it so much? And I think that's a good question. I'm not going to give you answers to that. That's like your exercise, homework exercises to figure out why. And I think it's also a little healthy to think about what's going to happen at the LHC. So there are two sorts of things that can happen at the LHC. One is that supersymmetry will be discovered. That's going to be completely fantastic. I'll be very surprised because I think it's a lot to ask for because it's a very, very beautiful extension of the standard model. But I mean, there's really no reason why nature should necessarily be going this path. The first thing that one would have to do, of course, is to establish that this is indeed supersymmetry that's discovered. But that would, of course, be really wonderful. Any new things that we find at the LHC are going to be really interesting. The other option is that the LHC does not discover supersymmetry or anything else. So then what are we going to know? You already had a great set of lectures on naturalness. We'll know that the Higgs mass and the standard model is tuned at the level of about 10 to the minus 3, let's say. And then what do we do with it? I think it's not there's no clear answer to that. The question is, how unnatural is unnatural? So if you're faced with a fine-tuning of 32 orders of magnitude, everyone agrees that this is a major problem. If you're faced with something that's around 10 to the minus 3, what do you make of it? The answer to that is not entirely clear. I mean, it's not clear that you need to change paradigms completely and abandon the idea of naturalness, for example, because the standard model is unnatural at this level. So depending on how things go at the LHC, we could be learning a lot, or we could be learning very little from a theory point of view. So why do we still want to do this? And why do we want to talk about supersymmetry? So, I mean, one reason is that I was asked to do that by the organizers, so that's just blame them. I mean, I'm just doing my job. But it's a very, very beautiful theoretical idea. I'm sure all of you know that. It's the only possible extension of space-time symmetry in 4 dimensions. And I'll give you some, I'll I'll start by giving you some reasons that kind of go from the theory to the more and more practical reasons for why we think about supersymmetry. And these are, of course, practical in the sense of high energy physics practical. I mean, it's not really applications, real applications that we're talking about, but things that matter to us, particle physicists. So I think that one of the main things to keep in mind is the revolution of 2012. Up until 2012, the only particles we knew were spin 1/2 particles and spin 1 particles. And there was no understanding, there still isn't, of some deep reason for why these are the structures that we see. Then comes the Higgs. The Higgs is the first fundamental spin 0 particle. And again, it's completely unrelated to the spins that we've seen before. Supersymmetry gives us a chance to relate these different spins. It relates in its minimal form. It relates a spin 0 to a spin 1/2. It relates a spin 1/2 to a spin 1. And so we get some relations between all the different spins that we observe. And maybe there's the hope of going towards a more fundamental understanding of what is spin. And given that we have the Higgs, that's a really important direction to go. So that's one thing. Essentially what it does is it makes a scalar behave like a fermion. This is a theme that we'll see recurring many, many times as we go on. And the fact that it makes a scalar behave like a fermion somewhat is exactly the thing that leads us to think about naturalness and SUSY as a solution to the naturalness problem. So the reason that supersymmetry cures the quadratic divergence in a scalar mass, so without supersymmetry, delta m squared would be given by something that starts with a quadratic divergence. With SUSY, this is just not there because it relates scalars to fermions. So that's a practical advantage of supersymmetry for us. And then there are other ones. Supersymmetry can supply dark matter candidates. It can supply new sources of CP violation. These are all things that we need. But the emphasis here should be on the can. I mean, it can do that, but it doesn't necessarily do that. And that brings me to the point which is somehow not completely appreciated, which is supersymmetry is really not a model. When we talk about supersymmetry as an extension of the standard model, we're not talking about a model. We're talking about a framework. We're talking about a symmetry. And there are many possible extensions within this category, which is one of the reasons why it's actually useful to think about it. But from the point of view of extending the standard model, it's a truly interesting direction of extending the standard model. You can think about the other directions, and here I'm being a little tongue-in-cheek. I don't mean it completely seriously, but a little seriously. You can extend the standard model and solve the naturalness problem by introducing new strong dynamics. But to some extent, we've seen strong dynamics before. We have QCD. Strong dynamics is something that we, in compositeness, are not things that we have never seen before. You can think about extending space-time symmetry by extra spatial dimensions, but that's, again, something, we have 3 dimensions of space. We know what a dimension of space is. So to some extent, we've been there and done that. With supersymmetry, this is a completely new ballgame. It's a symmetry that relates a fermion and a boson. And in this sense, it's a completely new and very exciting idea. In some ways, it's a bit of a quantum symmetry. Before you talk about quantum mechanics, you don't really care about the spins of particles. So in some sense, this is a symmetry that's very special to the quantum world. So it's something that's very interesting to think about from a theoretical point of view. But then whether it's there or not, it's been a very useful thing for particle physics. And there are two areas where it's been useful. The first is collider and other experiments. So you know that without some clear direction of things that you're searching for, it's very hard to find things at the LHC. You really have to be ready for the things that you want to discover. And supersymmetry, precisely because it's not a model, but rather a framework, gives you a whole set of possibilities that have been guiding LHC searches for a long time. So people have been looking at missing energy, they've been looking at displaced vertices, they've been looking at long-lived particles, even charged particles. So all these things are things that are realized in different scenarios of supersymmetric extensions of the standard model. So they've really been guiding the experimental program in many different ways. That's one area. Another completely different area is the area of which is much more theoretical. So on the theory side, it's been a great lab for strong dynamics. So as we'll see, when we think about supersymmetric theories, we can find all sorts of interesting behaviors that theories of strong coupling can exhibit. And the reason that we can do that is because the theory is very constrained. Because it's so constrained, there are many things that we can say compared to a theory without supersymmetry. And the key point here is holomorphy, which is something that we're going to talk about a lot. And again, holomorphy is exactly tied to this thing that I already mentioned, which is the fact that supersymmetry actually makes a scalar behave somewhat like a fermion. That's really tied to the idea of holomorphy. So roughly speaking, the plan for this is to start, the plans for the lectures are to start at the very beginning. I'm going to start with the basics. We're basically going to discover supersymmetry through a very innocent, the simplest sort of model that you can think about. Then we'll move on and introduce superspace. Then we're going to talk about the standard model, or the supersymmetric standard model. I'll be fairly brief here because I think that part you already heard to some extent and is quite easy to learn from all sorts of sources. But then one thing that I'll emphasize there is the mediation of supersymmetry breaking. And once we do that, we'll move to talk about the second part that I mentioned here, which is the understanding of strong dynamics. So here I'm going to talk about supersymmetric UCD and mainly mention exact results and duality. And throughout, I'm just going to restrict myself to n equals 1 supersymmetry, the minimal amount of supersymmetry in 4 dimensions. Okay, so after this introduction, let's start. So as I said, I'm going to start with a very simple model, just because I think that very often when you talk about supersymmetry, the first thing you see are so many indices and spinor notation that it just obscures all the physics. So I want to start with something really, really simple so that the physics is very clear. Okay, so the theory that I want to write down is just a free theory with a Dirac fermion, and I'm going to call it psi. It has mass m, and two complex scalars that I'm going to call phi plus and phi minus, and they also have the same mass m. And the Lagrangian is just the very simple Lagrangian of this free theory. There's the kinetic terms, d mu phi plus star, d mu phi plus. Same thing with plus replaced by minus. The mass term, of course. And same thing for the minus. And we also have the kinetic term for the fermion. And that's all. So this theory, which is a very simple theory, is a supersymmetric theory. So let's see why that's the case. And the thing that I want to start from is stuff that you're probably very familiar with, but let me still remind you of that, which is just deriving Lorentz symmetry or space-time symmetry. And then we're just going to extend that. Okay, so we're looking for space-time symmetry. And the thing that we need to look for transformations on the fields that keep the action and the equations of motion invariant. So the fields transform, but the EOMs are invariant. And when since we're talking about space-time symmetries, we want to have coordinate-dependent transformations. I don't mean coordinate-dependent transformations. I mean that the coordinates transform. Okay, so let's start by talking about translations. So under a translation, x mu goes to x mu plus a mu, and the field phi plus a minus, the two scalars, just go to phi plus minus x minus a mu. And for small transformations, for infinitesimal transformations, this is phi of x minus a mu d mu phi plus or minus. Now we can do two transformations. We can first of all change phi. We can first of all take x to x plus some a, and then we can do another translation with a different parameter b. And of course, when we do these two transformations one after the other, the order of doing them doesn't matter. So what we get is that the commutator of delta A and delta B acting on phi vanishes. This tells us that the corresponding generator, which in this case is momenta, this tells us that the momenta commute. P mu and P nu, this commutator vanishes. Now, if you can't remember how the momenta are related to the translations, let me remind you. So this is a global symmetry. Whenever we have a global symmetry, we have another current. We can look at how the action transforms and find that there's a conserved current. In this case, we have four currents because the transformation carries an index mu. So for each mu, we have a current. And this current satisfies d nu j mu nu equals 0. This tells us that there is a conserved charge because we can look at Q nu, or Q mu in this case, which is d3x j0 mu. And we see that taking the time derivative of Q mu is 0. So we have a conserved charge. In this particular case, the Q's are just the momenta. Okay, any questions about this? By the way, if you have any questions at any point, just interrupt me. Okay, so we just remembered how we derive the commutator, the algebra of two translations, starting with looking at what happens to the fields, what happens to the commutator of two translations, and then what it implies for the generators. We can do, of course, exactly the same thing for the remaining Lorentz generators. So we can go through this for the Lorentz generators. And I'm not going to do that in any detail, but let me just remind you. So for Lorentz, we look at x mu going to x mu plus omega mu nu x nu. These omegas are omega ij's for rotations, and there are omega 0I for boosts. And once we consider them, and you can work this out yourself and look at the commutators of two transformations like this, you find the algebra of the Lorentz of the rotations and boosts. So this is equal to I G mu rho J mu sigma plus all the other permutations. So this is just a quick reminder of how we see Lorentz symmetry in this very simple case. Any questions? Okay, so now let's look at this Lagrangian, which I already erased. And we've extracted, it seems, all the space-time symmetry. But there's actually more symmetry that's hiding there. So what else can we do here? What sort of other transformation? But actually, before I do that, I wanted to talk about the spinors. So far, I just talked about the scalar field. Let me also talk about how the Lorentz transformation acts on the fermions. So let me talk about, let's consider the field psi x. Under these transformations, it goes to psi prime of x, x prime. So now not only the x's transform, because we have a fermion field, the fermion field transforms as well. Now, actually, we can divide this 4-component spinor into two parts, which we can call psi L and psi right. And these upper components and lower components have different transformations under Lorentz. So what are these? So psi L goes to psi L prime, which is equal to 1 minus I theta I sigma I over 2 minus beta I sigma I over 2 psi L. And here, the beta, these guys label the boosts, and these guys label the rotations. So omega ij is epsilon ijk theta k. So these are angles, and these are the boost parameters. And this is what happens to psi L under rotations and boosts. And psi r goes to psi r prime, which has the same minus here, but the opposite sign here. So under the Lorentz transformation, the psi L's and psi R's transform differently. And that's a motivation to work with two-component spinors. So it's going to be very useful to think about two-component spinors instead of working with four-component spinors. Now, that's actually very useful because, as we know, the standard model is not a chiral theory. So it's a very natural thing to work with two-component spinors with left chirality and right chirality. Okay, so in fact, we can write every right-handed spinor in terms of a left-handed spinor, and vice versa. So let's remember how to do that. So I can write a right-handed spinor, psi r, as I sigma 2 chi L star, where sigma 2 is just the Pauli, the second Pauli matrix, of course. And I can also write this as minus epsilon chi L star, where epsilon is the matrix 0, minus 1, 1, 0. Once we do that, our Dirac fermion psi can be written as some, let's say that I start with a, okay, any Dirac fermion I can write as psi minus and minus epsilon psi plus star, where both these guys, both psi minus and psi plus, are left-handed. So we can write all our fermions as left-handed fermions using this notation. And now I can write my simple model again in terms of left-handed fermions. So the Lagrangian that we wrote down before has the fermion that has the scalar part, L of phi plus phi minus. Then we have psi plus dagger I sigma bar mu d mu psi plus the same thing with plus replaced by minus. And finally, there is the mass term, which has this form, psi plus t, epsilon psi minus plus plus and minus exchanged. And the thing that I defined here is this, I'm going to use two sets of sigma matrices, the unbarred ones, which are just the unit matrix, and then the sigma i's, and sigma bar mu, which is 1 and minus sigma I. So now the former Lagrangian that we had is written in terms of two-component left-handed spinors, and we see that the mass term actually connects the plus and the minus, and apart from this mass term, they're independent, and the plus and the minus don't talk to each other. Now we immediately, okay, and now, sorry. So now that we have this new notation, we can look at this Lagrangian and ask whether there is another symmetry that we haven't talked about before. So indeed, there is one. So we can do the following thing. We can take a constant anti-commuting spinor that I'm going to call, it has two components, Xi1 and Xi2. So each one of these is a Grassmannian variable. And we can consider the following transformation. Delta Xi of phi plus is equal to square root of 2 Xi t epsilon psi plus. And the same thing with plus replaced by minus. And delta Xi of psi plus equals square root of 2 I sigma mu epsilon Xi star d mu phi plus minus square root of 2 m Xi phi minus star. And again, the same thing when we replace the pluses with the minuses. Okay, now you can check, and this is a little exercise that's very useful. You can check that these transformations are a symmetry. So this is a symmetry of the Lagrangian. What does the symmetry do? It replaces, it takes a scalar into a fermion and vice versa. So that's a new sort of symmetry, and that's precisely supersymmetry. So we've discovered supersymmetry in this very simple model. Okay, so there are a few things to note about the symmetry. The first thing to note is that the mass m needs to be the same between the phi and the psi. The fermion and the scalar need to have the same mass, otherwise it's not a symmetry. When you do this little exercise, you'll discover that that's the case. The other thing to note is that for m equals 0, this model splits into two halves. There's the part with the phi plus and psi plus, and there's the part with the phi minus and psi minus, and they actually don't talk to each other. And actually, each one of them is the most minimal supersymmetric theory. This half and this half. Okay, the third thing to note is that this is a space-time symmetry. And the reason is that this transformation involved a spinor Xi, and so this is something that carries a Lorentz index. So there is an index, there is a spinor index on Xi, so this is necessarily a space-time symmetry. And there's another thing that we can observe about this, which makes it even clearer that this has something to do with space-time symmetry, and that's the following fact. So that's another exercise for you. So you can ask yourself what happens when you do two transformations of this sort in succession, and then take the commutator. So I can do a transformation with Xi and a transformation with eta. And the commutator of these transformations acting on phi plus, for example, is equal to a mu d mu phi plus. So what have we found? We find that the commutator of these two of these new transformations, the commutator of two supersymmetry transformations, gives us translation. So obviously, this is an extension of space-time symmetry. And that's, of course, a very profound result. Again, we can think about what does this mean in terms of generators. So how do we find the generators? Just like before, we have a symmetry that's with a symmetry parameter, a transformation parameter xi alpha. That means that we have a set of currents J mu alpha such that d mu J mu alpha equals 0. And if we integrate over J0, so this is J0 alpha, we get a conserved charge. Yes?
One question, when you have to commute between the two symmetries, which acts on phi plus, how do you get the mu into the equation?
How do I get this one? This one here?
I mean,
Yeah, that's an exercise for you. Yeah, right. That's a good question. It's completely, I mean, it's not something that you would see right away. You just have to work out the details. So that's something that I'd like you to do and verify that that's the case. Okay? But once you've done that, you see that what you get here is just a translation. And if I translate that to what happens in terms of the generators, what we'll find is that, again, we construct the SUSY generator just as we constructed the generators for translations, for example. And then what this thing means is that the commutator of two of these generators, Q alpha and Q beta dagger, this thing is equal to 2 sigma mu alpha beta p mu. So that's a result that I'm not deriving. Again, you can derive this yourself. It basically follows from this, but you can sort of see that this is what's happening. I mean, essentially, what we have here is in this delta xi is basically xi times the generator, and here you have eta times the other generator, and the anti-commutator and the commutator of these guys, because these guys are anti-commuting, implies an anti-commutator between the two Q's. Yes?
When you wrote down C psi plus earlier, the change in the Fermion, just what I thought. But the first term looks more like a vector than a scalar.
The psi plus?
Yeah, so there was a term with sigma mu in it. And
Oh, there was. Oh, you mean when I gave the transformation?
yeah.
Okay. So the transformation of. So you're asking about this guy, right?
Yeah, so like there's two terms.
Okay.
One,
Okay. So what can this thing be? Okay, it's something that involves this guy, which is a spinner. So there necessarily has to be a scalar that appears here. Okay, because this guy is a fermion. And then you're asking, okay, so the thing that you're really asking about is why, up to some constants that I don't care about, the structure here was sigma mu epsilon xi star and d mu phi plus. So the short answer, so I guess the thing that seems confusing is that we have the sigma mu appear here, and the derivative of phi that appears here. So off the top of my head, I don't have any good explanation for why that's the case, except to say that this is the symmetry that we can find. Okay?
transformation conformated Fermion is spin 1.
This is a transformation. We only have a spin 1/2 here and a spin 0. Okay? Now it's true that this looks like a vector because we're taking the derivative, but the way to really see this is just to look at the Lagrangian and ask what is the symmetry that you have, and this is the symmetry that you have. Okay? Okay, more questions? Yes?
So physically basically what the commutator means is I have a fermion sitting here, I do a supersymmetric transformation on it, I have a scalar at the same place, I do one more transformation on it, I have the same fermion somewhere else.
Okay, so the question is what does it mean to what's the physical meaning of this transformation? I don't think that, so at the end of the day we get a translation here. It just means that everything, there's a translation on everything, right? All the coordinates shift by something. Okay, it just means it's not so much, you can view this as a transformation on the coordinates of the fields. It's not that we're moving one thing from, relative to something else. Everything, there's a translation on everything. Okay? Okay. Good. So from this, what we really see is we see that supersymmetry is an extension of Poincare symmetry. So it's an extension of space-time symmetry, and thus it's got to be a very profound theoretical structure. Okay. A few more things that I want you to note about this symmetry in this very simple toy model. So we already said that we have here actually two halves. There's this part, and only the mass term that connects them. But you can see that here we have the same number of degrees of freedom. There's 2 degrees of freedom in psi, there's 2 degrees of freedom in phi, because it's a complex field. And I'm not going to show that in full generality, because I want to keep this very, very simple. But this is something that's going to hold completely generally. So we are always going to have the same number of fermionic and bosonic degrees of freedom. Yes?
It sounds like it's more of finding a symmetry between scalars and fermions. Why do you say it's an extension of Poincare?
Oh, because here I took, so this is what happens to a scalar field under translations, right? Under a translation, the field transforms exactly in this way. And here I took 2 of these new transformations, applied them one after the other, and then subtracted the opposite ordering of doing that, and I get translation. So we see that doing these 2 new transformations in succession reproduces translations. So it must be an extension of Poincare. In other words, what do I mean? I can ask the following question. So I think I looked at Nathaniel's lectures, and he talked about the Coleman-Mandala theorem. So what does the Coleman-Mandala theorem say? It says, suppose we want to take Lorentz and Poincare, or Poincare symmetry, right? There's all the different commutators that we know, p mu equals 0. There's the commutator for the j's, which we already wrote down. J and p commute, blah, blah, blah. And then we're asking, can we add some new generators that don't commute with some of the Lorentz generators and translations? And can we get some non-trivial structure? Of course, if we have a new generator that commutes with all of the generators of the Poincare algebra, this is something that's not an extension of Poincare, right? I mean, it just doesn't talk to them. But here we find something that satisfies some non-trivial commutation relations that involve the translation generators. So this is an extension of Poincare symmetry.
So theoretically, we could come up with some new operators whose commutator we could then find is proportional to, let's say, delta C.
Well, if you do, that would be great. I mean, this is a completely legitimate question, right? I mean, in this very simple model that we wrote down, we have this new symmetry, and there's nothing else that you can find that extends Poincare. Okay, I mean, this is just coming from many years of work that people did, right? That's the maximal thing that you can have. You can have more complicated models with more fields where you have more supersymmetries. But the thing that holds generally, and that's the loophole to the Coleman-Mandala theorem, is that if you want to extend Poincare symmetry, the only way to do that is to involve anti-commutators. You have to go to something that's not an algebra, but a graded algebra. And here what happens is precisely this. We extended Poincare, the Poincare algebra, by adding things that anti-commute. Okay? So that's what happens here. Yes?
It seems that in this case it appears when you transform the fields in certain way. But does this symmetry appears also at the level of ace matrices? I mean, without talking about fields at all. And you can prove that it's also supersymmetry.
You want to talk about what?
Yeah, for example, at Weinberg, you have like, you talk about states and ace matrix before talking about fields.
Oh, absolutely, yes. I mean, you can actually, right. So here I talked about fields because this is the thing that most of us are used to. I mean, writing down some field theory. But you could, you can even, you can talk about quantum mechanics, okay, with supersymmetry. You can just take a quantum mechanics theory and make it, and supersymmetrize it. So absolutely, yes. More questions? Okay. So, right, so where were we?
I have a question.
Yes.
So is there a proof that this is the only symmetry that you can find between fermions and scalars?
Well, actually, it's here I'm talking just about minimal supersymmetry. And you see that I just introduced one spinor generator. In other words, I'm allowing just one parameter xi. You can introduce more supersymmetry. You can introduce, but there you have to look at a more complicated model. So when we start to introduce more SUSY generators, here we just related a spin 0 and a spin 1/2 particles. If we also have spin 1 particles, then we can relate all of them together. In 4 dimensions, this is what's called n equals 1 supersymmetry, and you can also have n equals 2 and n equals 4. And that's the most that you can have. This is the maximal number that you can have. Okay. But as I said, I'm only going to talk about n equals 1 throughout these lectures. Okay. Now, in our simple example, we already said that these guys had the same number of degrees of freedom. This structure is something that's called a chiral supermultiplet. And this is just one sort of supersymmetric multiplet that you can have in 4 dimensions. We're going to see them a lot. And I already said that we have the same number of fermionic n degrees of freedom that appear here. Okay, so now let's see something else, which is also very profound. So the next thing I want to talk about is the vacuum energy. So I'm still talking about our very simple toy model, or actually maybe not just, but okay. So let me take this result that we had over here and sandwich it between, and put it in the ground state. So we want to look at the expectation value of this anti-commutator. And what is this thing? So we have it over here up to 2 that doesn't matter very much. What we have here is sigma mu alpha beta 0 p mu 0. So we just get the translation sitting in the ground state. And you see that because the ground state doesn't carry any momentum, the only mu that can contribute here is mu equals 0. So this then is sigma 0 alpha beta. Sigma 0 is just the identity matrix. And you see that what you get here is delta alpha beta times the Hamiltonian. So this immediately tells us that the vacuum energy, this guy is just the vacuum energy. So we learned that the vacuum energy is 0. So in a supersymmetric theory, the vacuum energy is 0. And again, the important thing here was that this thing vanished. Why did it vanish? Because I said the theory was supersymmetric. If the theory is supersymmetric, it means that the ground state respects supersymmetry. That means that the supersymmetry generator annihilates the ground state. Okay? If supersymmetry were broken spontaneously, that would mean that the generator doesn't annihilate the vacuum. It takes it into some other state. Okay? But just from this relation, we found that the vacuum energy vanishes. So now again, that's quite a lot. So we're getting a lot from this very, very simple model. And there are two comments I want to make about this. The first thing is that this is a very promising result. Why is it very promising? Because you know, and you actually heard that in Nathaniel's lectures, you know that usually a vacuum diverges, right? If you start calculating loop corrections to the vacuum energy, you find something that's divergent. It's the worst divergent that we have, actually. It goes like lambda to the 4th. And now we find that this lambda to the 4th is multiplied by 0. So we get rid of the worst divergence that we have using supersymmetry. So that gives us hope that just like it took care of that divergence, we can take care of the quadratic divergence in the Higgs mass. Okay? So maybe it can cure the delta m squared quadratic divergence. And that's really the basis for the naturalness story with supersymmetry. Okay, now it tells us another important thing. It tells us
I'm sorry, can I ask a question
Sure.
before you go?
Yeah.
Could you elaborate on why that left-hand side is 0? Because we defined this conserved chart, right?
Uh-huh.
And then you're saying that applying that chart, that operator on the vacuum has 0 eigenvalues, so the vacuum doesn't have any
So what
that Q chart.
So what I'm saying is that if you have an exact symmetry, it means that if supersymmetry is an exact symmetry, then Q alpha on the vacuum is 0. Okay? And if you're confused about that, remember the story with electroweak symmetry breaking, or the Higgs mechanism. Okay? So suppose I have some U1, which is, so I have a theory with a U1 symmetry, and it's got a ground state at the origin. That means the U1 is unbroken.
Right.
Okay? What does the U1 do? The U1 generator rotates me in this direction. What does it do to the vacuum? It doesn't do anything. Okay? And this is something that we need to compare with the Mexican head potential, where this is my ground state. And when the U1 symmetry generator, what the U1 symmetry generator does is it takes me from one ground state to another. Okay? So as long as supersymmetry is exact, this thing vanishes.
Right, so that's why you were saying that if it's broken, then that's no longer true.
That's right. So as long as supersymmetry is unbroken, the vacuum energy is 0. Sure. Sorry.
In supersymmetric theories, there are going to be UN theories, and you said
No.
you're just doing
No, not
We're
necessarily.
just doing n equals 1,
Oh, we're just doing n equals 1 supersymmetry.
so it's a U1.
It doesn't need to, no, you shouldn't. This is, there's the n, we're doing n equals 1. Make this curly n. This is the number of supersymmetry generators. Okay? This has nothing to do with an SUN. It's a different n.
Or UN.
No, it's a different n. Yeah. Yes.
The distance question, so compared to normal purities, we now have that the vacuum energy is basically 0. So would it be possible to explain the smallness of the cosmological constant also via some supersymmetry framework, or?
Well, yes. So actually, before the cosmological constant was measured to be non-zero, people thought that the cosmological constant was 0, and then with supersymmetry, it would have been very easy to explain. But the next thing we're going to say is that supersymmetry has to be broken. It has to be broken because we saw before that fermions and bosons have to have the same mass. So that means that if we're talking about supersymmetry for the real world, we're not talking about supersymmetry. We're talking about supersymmetry, about broken supersymmetry. Okay? That's why supersymmetry breaking is such an important thing to understand. So, so we know that the cosmological constant, so supersymmetry does not give you a 0 cosmological constant because it's broken. So there's got to be some correction. Yes. Okay. Okay, so as I already said, we know immediately from what we said before. Before we saw that fermions and scalars needed to be degenerate. In our real world, we don't see fermions and scalars that are mass degenerate, so we know supersymmetry is broken. So we know that in the real world, Q alpha on 0 is not 0. Okay? And our vacuum energy is therefore not 0. And so when we're interested in thinking about supersymmetry, we'll have to look for supersymmetry breaking theories that give us some non-zero vacuum energy. And we can also say that the vacuum energy is an order parameter for SUSY breaking. So when we need to decide whether supersymmetry is broken or unbroken, we'll need to look at the vacuum energy. Okay, so that's the lesson here. So this is already a lesson for thinking about SUSY breaking, which is something that we're going to come back to. So we see that if we're looking for SUSY breaking, we need to look for the minimum of the potential. And essentially, the thing that we need to understand is V 0 or is V bigger than 0? So supersymmetry breaking is really simple. In a supersymmetric theory, you have scalars. So there's some potential for the scalars. If you want to decide whether supersymmetry is broken or unbroken, you need to look for the minimum of the potential and see whether it's at 0 or not. And then you know if supersymmetry is broken or unbroken. Okay? That's the lesson from this. Okay. So a very simple example of a supersymmetric theory. Let's give the simplest example of a supersymmetry breaking theory. Okay? And I'm not going to give you the full story here. We're going to complete the story a little later, but it's part of the story. So the simplest example of a SUSY breaking theory is something that's called the O'Rafferty model. And that's really one of the most important things that you need to do if you want to talk about supersymmetry breaking, is you need to be able to spell this name. And even now, I need to look at this, and I hope I didn't mess up anything, but let's imagine I didn't. So O'Rafferty introduced this very simple model of SUSY breaking, and I just want to tell you what it involves. It has 3 chiral supermultiplets that I'm going to call phi 1 and phi 2. And these are the scalars in these supermultiplets. And the potential for the scalars has the following form: phi 1 squared minus f squared plus m squared phi 1 squared plus 2 phi 1 phi 2 plus m phi 2 squared. And it's very, very simple to see that that the minimum of this potential is not at 0. Okay? The minimum of this potential is above 0. So this theory breaks supersymmetry. The thing that I haven't shown you is that this potential really follows from a supersymmetric theory. But that part we're going to do a little later on. Okay? So for now, I'm just showing you the potential. And you can already see a very simple thing. If I want to break supersymmetry, it means that I need to generate a non-zero vacuum energy. So I need a scale. I need to have a scale in my theory. And indeed, if you look at this model, you see 2 parameters that have some non-trivial mass dimension. This guy f has dimension 2, and there's also m, which has mass dimension 1. So I needed to put in 2 scales by hand in order to get supersymmetry breaking. And you can see that in some cases, for example, the vacuum energy is going to be of order this guy squared. That's the thing that sets the size of the SUSY breaking. Okay, so this is another little exercise for you to do. It's very simple. So you can show, for example, that for f smaller than 1/2 m squared, the ground state is at phi 1 equals phi 2 equals 0. Phi is arbitrary. And V0, the ground state energy, the 0 of the potential, is equal to f squared. So the vacuum energy in this case is equal to the square root of f, and that's the scale that comes in. So we see that SUSY breaking is necessarily related to the appearance of a scale. Now, later on, we're going to write down the full Lagrangian for this model. I just showed you the scalar potential, but then I'm going to tell you the full Lagrangian. And you'll then be able to work out the spectrum of this Lagrangian. So this is anticipating when write the full Lagrangian for this model. We'll see the following thing. We'll see that we have the following spectrum. So I'll write the full Lagrangian. We already know the potential. We already know that this is the ground state. And then we'll be able to show that in this ground state, the spectrum is the following. First of all, we have some massless guys. The massless guys are going to be one Yael fermion and two real bosons. And then we're going to have some particles with masses that are non-zero. And this is what we're going to have. We're going to have one Dirac fermion of mass m. And we're going to have two real bosons, two real scalars with mass squared equal to m squared plus or minus f. Just a second. So let me draw this here. So hopefully you can even see it. So this is what the spectrum is going to look like. First of all, I have at m equals 0. At m equals 0, like I said, I have two scalars. Now I'm counting real scalars and one fermion. And then I also have, let me say that here I'm putting mass squared. So at m squared, I have one fermion, which is of course a Dirac fermion because it's massive. And then here at m squared plus f, I have one scalar. And then here at m squared minus f, I have another scalar. So you see that what is the parameter for SUSY breaking here? It's f, right? If I put f equals 0, I go back to 0 vacuum energy. Supersymmetry is an exact symmetry. Then all these guys come together. Then we have a Dirac fermion and two scalars sitting together. Here we get splittings between the fermions and the scalars, and the splittings are proportional to f. Okay, now the counting is a little confusing because I didn't tell you the whole story, but this is roughly what happens. I mean, this is going to be very generic. If we break supersymmetry, what we'll find is that we have a splitting between the scalars and the fermion, and the splittings are going to be proportional to the SUSY breaking scale. Now there was a question, I'm sorry, before that the potential? Oh, you mean this phi? The one that's arbitrary? So I wrote down the potential before, and the thing that I asked you to do as an exercise is to minimize the potential. And the potential, where the minimum is, depends on the relative value, the relative size of f and m squared. So you'll see that for this choice, the ground state is here, and the value of this guy is arbitrary. Phi can be anything. Yes. Oh, I'm sorry. Phi, phi 1, and phi 2, and you just need to minimize it. Okay. You have to actually do the exercise in order to see this. There's something completely non-trivial here. Maybe I'm misunderstanding the question.
No, it's because in the potential I didn't see the dependence.
Maybe you just write it down again.
Oh, okay. Yes, you didn't. Yes, that's right. Okay, right. It doesn't depend on phi. The potential doesn't depend on phi. The reason it seems that, so it's completely trivial in this case that phi is arbitrary because we didn't see it in the potential. We'll see phi when we actually write the full Lagrangian. Okay? So you're seeing half the story. That's why it's confusing. Sorry. Okay, yes, there was something else.
There's a follow-up question. So why do we need this phi supermultiplet in this case?
Oh, again, because I haven't told you the full story. I mean, I told you the potential, but I didn't tell you the theory. I didn't tell you the full Lagrangian. Okay, so you have to wait a little bit. Yes?
Yeah, maybe you have an infant. Did you get Goldstone bosons here?
I'm sorry?
Did you get Goldstone bosons?
Oh, yes, that's a really good question. Thank you. So the question is about, do I get a Goldstone boson? Because you're right. I mean, I have a generator, Q, that acts on the ground state, and it's non-zero, right? So usually you expect a Goldstone boson. The only twist here is that this guy is fermionic, okay? So the thing that we get is a Goldstone fermion, okay? Precisely. This, I have a fermionic thing, an anti-commuting thing acting on the ground state, and that's precisely what it does. It gives me a Goldstone fermion. And this guy is sometimes called the Goldstino. So this guy is the Goldstino. And it's very, very important. And indeed, the fermion that you have here at m equals 0 is precisely the Goldstino. We're guaranteed, whenever we have SUSY breaking, we're guaranteed to have a massless fermion, which is the Goldstone fermion. Yes?
What's the physical meaning of F?
Of F?
Yeah.
It's, in this case, it's just a parameter that I put in by hand in order to get supersymmetry breaking. And its physical meaning is that it has two sorts, it comes in two places. It's the vacuum energy, and it's the splitting between fermions and bosons of the same supermultiplet. Any fermion and boson that are degenerate with exact supersymmetry are going to develop some mass splittings that are going to be proportional to this parameter F. Okay, so let's go on. Okay, so let me recap everything that we said so far. And see what we learned. So we said the following thing. We said that supersymmetry is an extension of Poincaré. It exchanges bosons and fermions. We saw that supersymmetric theories have evac ground state energy which is 0, and the bosons and fermions are degenerate. And we saw that with spontaneously broken supersymmetry, spontaneously broken SUSY, the ground state energy is bigger than 0, so you develop some scale, and the bosons and fermions are now split, and the splitting is proportional to the vacuum energy. And sometimes this vacuum energy is referred to as the SUSY breaking scale. Okay. So we talked a little bit about divergences. Let's say some more about divergences. And here I'm coming back to stuff that I think you did with Nathaniel, but let me go through it kind of quickly. So now we want to talk more about divergences. We saw that in the vacuum energy, we had 0 times the quadratic divergence. And then the next worst divergence that we can have is in a scalar mass, which can go like lambda squared. Now, this is really the reason why the Higgs is a problem. It's a problem because it's a spin 1 particle. Before the Higgs, we only had fermions. I'm sorry, spin 0. Thank you. So before that, we just had fermions. And for fermions, we never worried about fine-tuning, right? There wasn't any naturalness problem for fermions. And Nathaniel already explained why, right? Why don't we worry? Why is naturalness not a problem for fermions? Chiral symmetry, right? So chiral symmetry saves the day. We don't have this guy for scalars. And this is something that supersymmetry can cure. So essentially, the magic is that in a SUSY theory, the scalar mass squared is related to a fermion mass squared by supersymmetry, and then this mass is protected by chiral symmetry. So that's the reason why, that's the way that the quadratic divergence is cancelled. Now, the thing that's interesting is that we already said that supersymmetry is broken, right? I told you supersymmetry needs to be broken. So why do I care about this? I could say if supersymmetry is broken, then this nice property goes away because this doesn't hold anymore. The important point is the following. The important point is that if supersymmetry is only broken by mass terms, then delta m squared still has no quadratic divergence. So this thing is not spoiled, okay? And so let's see that. So let's see why this happens. So I start with some supersymmetric theory. I start with a SUSY theory. And in the SUSY theory, I have a scalar which has mass m0 squared. And I have a fermion which has mass m0. I mean, the scalar has mass squared m0 squared. And now I break supersymmetry. But I break supersymmetry by adding a mass term. So there's SUSY breaking, which is what we call soft SUSY breaking. Namely, I change this mass to m0 squared plus m tilde squared. Soft breaking, so far, is just a name. What we mean by soft breaking is that we change the theory such that the scalar mass is changed by some amount. And the fermion mass stays as before. You see that the breaking here is in terms of a dimensional parameter. We break supersymmetry, but we break it in terms of a dimensional parameter, which is this m tilde here. So now we can look at the quadratic divergence. So now I can look again at this delta m squared. So this is the correction to the scalar mass squared. And in principle, there is going to be some quadratic divergence here with some number. And then there's also a logarithmic divergence that goes like m0 squared times the log of m0 squared over lambda squared. These are the divergences that we can have. Now, what is this number here? I don't know what the number is, but I know that it must be proportional to m tilde squared. Because if I didn't have SUSY breaking, if I had exact supersymmetry, then m tilde squared would be 0, and I wouldn't have a quadratic divergence. So you see that just on dimensional grounds, this is impossible. Because there's nothing that I can write here that has the right form. It's something that needs to be proportional to m tilde squared, but there's no room for that. Because this is a correction to the mass squared, and here I already have lambda squared sitting, so there's nothing I can write down here. So I immediately see that this guy is just not there. So the lesson is that supersymmetry is so powerful that not only it protects the scalar mass squared, but even if it's broken by a soft parameter, even if it's broken by a dimensional parameter, it still continues to protect the scalar mass squared. Yes?
But you could write down m tilde squared divided by m zeros, right?
Not in perturbation theory. I mean, if you think about some perturbative expansion, there's nothing that would give me this negative. There's nothing in the denominator that I can write down. Okay. So there's nothing that we can write down that would reintroduce the reintroduce the quadratic divergence, and that's a property of soft breaking. This is soft breaking of supersymmetry. So this has to be contrasted with hard breaking. If I have a hard breaking of supersymmetry, I can reintroduce the quadratic divergence. Here, there is going to be a quadratic divergence. What does it mean, hard breaking? It means that I'm breaking supersymmetry not by a dimensionful parameter, but by some dimensionless parameter. Okay? So if I take some theory, a hard breaking means that we take the supersymmetric theory and we fiddle with one of the dimensionless parameters. And we'll give an example of that in a second. Okay, so let's, in order to see this happen, let's take some concrete model. And of course, we want to generate divergences here. So we need to introduce interactions. If we don't have interactions, nothing's going to happen. So I need to write down some interactions. So let me do that. So we just have 5 minutes left, but I'm going to do it anyway, or at least start. So here, what I want to show is the difference between soft breaking and hard breaking from the point of view of the divergences. So I want to introduce interactions. So I want to go back to our example, the one that we had before, the first example. So we had this model with phi plus and minus, and psi plus and psi minus. And I want to add a complex scalar that I'm going to call H. And because I want a supersymmetric theory, I know that if I introduce the complex scalar, I better also introduce a Yael fermion that I'm going to call H tilde. And now here's the theory. So in this theory, we have the kinetic part of the Lagrangian and the interaction part. And the kinetic part is very simple. I don't even need to write it down. There's the kinetic term for phi plus, and same thing for phi minus, and same thing for h, which I'm not writing down. There's the kinetic term for the fermions, so there's psi plus dagger I sigma bar mu d mu psi plus, and similarly for psi minus, and similarly for h tilde. And then I have the interesting part, which is the interaction part. And the interaction part has the following form. First of all, there's a coupling of the scalar to the fermions. So I have h psi plus t epsilon psi minus plus phi plus h tilde transposed epsilon psi minus plus phi minus h tilde t epsilon psi plus the Hermitian conjugate. And then I have something else. I have minus y squared times phi plus squared phi minus squared plus h squared phi plus squared plus h squared phi minus squared, and that's it. Now, this complicated structure is completely dictated by supersymmetry. So, for example, suppose I wrote down this term, this one little term, then supersymmetry tells me that I have to have all this extra baggage. Okay? There's absolutely no freedom here. And in particular, this parameter y, this coupling y, has to be the same for all of these guys. And this parameter has to be exactly the square of the y. No freedom. And once we have this Lagrangian, then we can calculate, and we're not going to do it now. And I think I'm going to leave it as an exercise because you already did it with Nathaniel, so you know it very well. With this Lagrangian, we can calculate the correction to mh squared, and we find that there's no quadratic divergence. So now, what are the things that are interesting about this? So here I didn't write down the mass terms for these guys. The point is that this continues to be the case even if now psi plus and psi minus have mass m, but phi plus has mass squared, which is equal to, phi plus has mass squared, which is m squared plus m tilde squared. Okay? And phi minus has mass m squared plus some other m tilde prime squared. In this case, if you calculate the correction to the Higgs mass, it's still going to vanish. So here we still calculate this guy and we still get no quadratic divergence. However, if we do, so this is soft breaking. This is soft breaking because I just took the masses and changed them. But I could do a hard breaking. What does it mean to do a hard breaking? So let's put it here. So a hard breaking would be to take one of these parameters and change it into something else. For example, keep y here, but change this guy to y tilde, and keep this guy as y. Or keep all these guys as y and change this guy to some other thing. If I do something like this, if I do a hard breaking, then I'm going to generate a quadratic divergence. So versus hard breaking, where we change y or y squared, then we're going to get some non-zero quadratic divergence. Okay? Now, this is a very easy calculation. You can all do this one loop calculation and convince yourself that this is the result. I'm not going to do it next time because I think you already saw part of it. Plus, you know, you need to keep busy, so it's a good idea to do that. And I think that with this, we're going to conclude for today. But more questions?
Yeah, why would we ever do hard breaking if it generates a...
We wouldn't.
We wouldn't.
Yeah. I mean, that's why you want to do it once and then you just don't want to do it. But it's exactly the same story as with any other symmetry. When we talk about it, usually we talk about, or sometimes well, most of the time we talk about a symmetry and a symmetry that's spontaneously broken, right? We don't talk about a symmetry that's explicitly broken because it's usually not very useful for many things. Actually, this is almost correct because what we'll see as we go on is that sometimes it is very useful to think about explicitly broken symmetries because we can still get all sorts of things from this. But in any case, what I want to say here is that the symmetry is, for the purposes of naturalness, we don't want to break SUSY explicitly. Plus, if we break it explicitly, it means that our Lagrangian really is not supersymmetric. So what do I do about it? I mean, it's just not very good. Still, sometimes if the breaking is small, it can be good because it lets me parameterize the amount of SUSY breaking, the sizes of SUSY breaking effects. But the most useful thing to think about is spontaneously broken symmetries in general. Yes?
There's a follow-up question. So if you softly break supersymmetry to generate the standard model masses, would you say that we still need some sort of fine-tuning by this procedure, or is it more or less natural to just softly break to generate the masses?
If you want to use SUSY breaking to generate the masses of the...
the observed masses of the standard model.
Oh, the fermion masses. See, the fermion masses are not supersymmetry breaking parameters because they're protected by a chiral symmetry. Okay? So, you know, maybe there's something smart that you can cook up, but most of the time this is not going to happen. I mean, the rule is, when we have a quantum theory, everything is allowed. It's a very liberal theory. Everything that can happen will happen when we talk about quantum corrections. And usually the worst thing that can happen does happen, right? Okay, that's the fact of life. So if something can diverge, it will diverge, unless there's something that protects it. So in the case of writing supersymmetric extensions of the standard model, you'll be adding lots of scalars or Majorana fermions. These guys are not protected by any symmetry. So once we have SUSY breaking somewhere, the scalars and the Majorana fermions can get mass. But the chiral fermions cannot get mass because they're protected by a chiral symmetry. So they're going to stay put. More questions? Yes?
Maybe back to the fundamentals. I was wondering, what happens to the Lie group structure? Like, you just gave us infinitesimal versions of these new generators.
Oh, you're asking about the finite?
The algebra structure,
Yeah.
right? Because you need the
Yeah.
anti-unitarians. exponentiate.
Yes, yes, you can absolutely do that. Yeah, I mean, I didn't want to get into this, but you can look at the exponents of the q's and write down the full algebra, and basically what happens then is that I have to look at e to the I xc dot q essentially, right, or xq. So this is just going to be q alpha, xc alpha, q alpha, plus the Hermitian conjugate of that. And in the limit of infinitesimal x's, which, you know, is a funny thing to think about, but I can look at the infinitesimal form of this. So you can do this, but it's not something I will have time to discuss. Okay, I guess, you know, it's with these temperatures after lunch, okay, we need to finish here.